Hi, welcome to the Urban Computing Skills Lab for CASPS 2016. My name is Federica Bianco. I will be your instructor in the Principles of Urban Informatics class, which is one of your core classes in the fall. So we will meet in person very soon. In the meantime, we're providing these lectures so that you can master some of the basic concepts of statistics and probability that will be necessary to succeed in the classes in the fall and in the curriculum of urban informatics in general. Today, we will cover some concepts about probability. Particularly, we will focus on continuous probability distributions, and we will look at a couple of theorems that are very commonly used in data science, in statistics, and in urban data science as well. All of the material that I will use today for this class, all of the slides, as well as the code that produces the plots that I will use in the slides, and an IPython notebook that we will use to understand some of the concepts that we will cover, are going to be available to you online at this URL. And you can always contact me. Here is my email address. So let's begin by reminding ourselves why we are focusing so much on probability and statistics when we try to prepare you for learning about urban informatics. Statistics and probability allow us to make inference about a population based on what we know about a sample. In other words, if we were able to probe the entire population of people that we're interested in finding out things about, if we were able to probe to look at every building in a city or every city in the world, we wouldn't really need statistics. We would just be able to count events and facts about our population. But statistics allows us to take a subsample of a population, to take a subset of the people that we're interested in, find out things about that subset, and by extension, understand how the things about the population work. So it is very important to understand that when we work with statistics, we're working with subsets of the entire population to be able to make inference about the population. Some of the inference that we can make, for example, is a detection of outliers. Events like Hurricane Sandy is an outlier in weather patterns, or maybe the probability of meeting a dinosaur in New York, that would definitely be an outlier. We can do prediction based on the knowledge and the current state of the sample that we are testing. We can, for example, be able to predict disease outbreaks based on the purchase pattern of medicines. We are able to understand what the average is, and maybe even get to causality and understand what causes certain phenomena. For example, if we look at the incidence of asthma in two different areas of New York City, the average number of people affected by asthma, maybe we're able to see how that relates to things like traffic patterns and construction, and able to get to a cause from the effect. So far, you have covered discrete distributions. Particularly, you have focused on two very common discrete distributions, the binomial distributions and the Poisson distribution. The binomial distribution describes events that have only two possible outcomes. We generally refer to them as success and failure, although we don't necessarily imply to give a positive or negative connotation to either. A very simple example is when you toss a dime, and you can have either head or tail. If the dime is fair, the probability of having head or tail will be 50%, and then you repeat the experiment many times, and that probability of getting however many heads or tails is described by a binomial distribution. The Poisson distribution is a very common distribution which we use in count statistics for events where we are counting number of things. This could be a number of events, for example, the number of accidents at a particular crossroad at a particular time of the day, or the number of floors in Manhattan buildings. It so happens, in fact, that the number of floors in Manhattan buildings is distributed fairly well, like a Poissonian distribution. I downloaded data from the Pluto data set for this particular plot, and again, the plot is available, and the code that makes the plot are available on GitHub. And you can see this histogram, which is basically describing the probability distribution, where you have the number of floors at the bottom on the x-axis, and the number of buildings with that number of floor on the y-axis. And on the left side, you have the distribution of number of floors only, and on the right side, you have an overplotted Poisson distribution. You can see that the two plots are fairly similar. In fact, in the course of data science and principle of urban informatics, you will learn to say how well the Poisson distribution describes this particular distribution of floors, but this is not for today's lecture yet. So when you have a probability distribution like the binomial or the Poisson distribution, you can tell what is the probability of a particular outcome. So for example, I can say, what is the probability that the number of floors will be 2? And that will depend on the parameter of the Poisson distribution. The Poisson distribution has a single parameter, lambda, which describes it. And I will get a number for the probability of getting 2 floors in a building, or for the probability of getting 7 floors in the building. However, I cannot talk about the probability of getting a fractional number of floors. Intuitively, this should make sense because floors only come in integer units. You can have 1 floor, 2 floors. It doesn't really make sense to talk about 0.5 floors. It doesn't really make sense to talk about 3.5 accidents at a crossroad. And in fact, Poisson statistic only is defined for discrete values. This is why we're talking about discrete probability distributions. Intuitive, as I said, this makes sense because we are counting numbers, we are counting events, we are counting objects, and those only take integer values. And mathematically, it makes sense because in both the binomial and the Poisson distribution, you have a factorial. And factorials are functions that are only defined for integer numbers. So what if I want to describe the probability of a continuous variable? A continuous variable is a variable that can take any value perhaps within a range, or maybe any value in the real numbers domains, which means between minus infinity and plus infinity. So in that case, we're talking about continuous probability distributions. Let's look at a very simple and actually very common continuous probability distribution. The simplest continuous probability distribution is the uniform distribution, where what we are saying is that the probability of an event being within a certain range is constant. It's the same at all points in the range. It is hard to really imagine a physical process that naturally complies to this distribution. However, it's extremely common because it's used in Bayesian statistics when you have a prior and you don't know a lot about the situation, you don't have a very informative prior, but you want to perhaps maybe just limit the range where your variable will live. So in this case, we have a probability distribution that I defined as C, constant, between 0 and 5, and 0 everywhere else. So the probability of my outcome being between 0 and 5 is going to be something. The probability of my outcome being less than 0 or more than 5 is going to be 0 exactly. The something that the probability is going to be a number that is driven by the fact that the probability under the curve has to be 1. As we have covered in the previous lecture, probability for anything to happen, by definition, has to be 1. Therefore, that means that the integral under this curve, the area of this rectangle, has to be 1. And to make the area of that rectangle 1, with the x-axis going between 0 and 5, you're going to have a probability of 0.2. So this particular uniform distribution has a probability of 0.2 between 0 and 5, and 0 everywhere else. So let's look at the probability of something, for example, being less than 2.5. If I have this probability distribution, I can tell you what is the probability that my event will be between 0 and 2.5. Simply between 0 and 2.5 means the event has to live half the way, in half of the realm of possibilities. So the probability is going to be the area under the curve that is limited by this 2.5 boundary. This is half of the total area. The total area is 1. So the probability of my outcome being between 0 and 2.5 is simply 0.5. Let's get a little smaller. What if I'm interested in the probability of my outcome being between 0 and 0.5? Now I have a smaller rectangle. Again, the probability is going to be the area of this rectangle. And in this particular case, the probability is going to be 0.1. Those of you that are familiar with calculus and with differential calculations are seeing where I'm going with this, probably. If I keep shrinking the interval, if I keep shrinking the region that I'm interested in knowing what is the probability of being in that region, I'm going to end up with a line. I'm going to end up with asking myself, what is the probability that I will get a value of, for example, exactly 1.0? And that probability is going to be 0 because my rectangle has become a line, and a line has no area. So the core difference between continuous and discrete probability distributions is that for a continuous probability distribution, I actually cannot define the probability of my outcome being exactly a number. That is always going to be 0. I can only define the probability of my outcome being within a region. And when I want to compare probabilities, I have to compare similar regions. I have to compare similar bins of the histogram or similar regions of interest. One thing that we will do very often is going to be looking at the probability of things being larger than something or smaller than something. Let's briefly look at a slightly more realistic and more common continuous distribution, more physically natural continuous distribution. A very common continuous variables that we may be interested in is distance or location. So a common example to describe continuous distribution is a dartboard. If I am playing darts, and my only interest in this case is to get to the center, to get to bullseye, I don't really care about the segmentation of the dartboard, having different points at different angles. I'm going to try and aim for the center, but I don't have a precise aim, so my darts are going to end up being distributed at some distance from the bullseye. If I am a decent player, the majority of the darts will be near the center, and they will be progressively fewer as I move away from the center. If I plot this as a surface, and the distance, and if I plot the distance between each dart and the bullseye as a surface, I'm going to end up with something like this. This is a very common shape for a lot of probability distributions that we are very interested in and that are very commonly used in statistics and data science. Right now, on the y-axis, I have the number of darts, but if I normalize that shape, if I normalize that surface so that the volume underneath it is 1, then that becomes a probability. This shape with a single peak and what we call a bell shape for a probability distribution is common to a lot of interesting probability distributions, and particularly it is the shape of the Gaussian or normal distribution, which we're going to focus on next. So let's go back to a two-dimensional space where we have the probability distribution as a function of one variable only. But let's focus on the Gaussian distribution or normal distribution. Here you have the function of the Gaussian or normal distribution. Because, as I said, you cannot define the probability distribution, the probability of an exact number, an exact outcome for continuous probability distributions, we generally talk about the probability distribution in terms of probability density function. So on the y-axis here, you have the probability density function, and on the x-axis, you have all the possible outcomes. For the Gaussian or normal distribution, the outcomes can go from -infinity to +infinity. Let's take a close look at the formula for a second, because there are several interesting things in the formula of a Gaussian distribution. The first piece is just a normalization, which means that when I multiply my probability density function, when I multiply my histogram by this, I get a probability under the curve of 1. I go back to the rules of probability where the probability of anything happening has to be equal to 1. This allows the probability of anything happening being equal to 1. The second piece has an exponential, and then the exponent of that exponential contains two terms that are the two parameters of the distribution. The parameters of the distribution are the mean and the standard deviation, mu and sigma. We usually use Greek letters to refer to them. And notice that the possible outcomes, the x, the vector of my the possible outcomes of my experiment, only appears in a term in quadrature here. This infers symmetry to the distribution. What that means is that my distribution doesn't know really if this number x minus mu is positive or negative. It only knows about the absolute value of it. Therefore, the Gaussian distribution is a symmetric distribution, symmetric around the value of mu, which is the mean. And the parameter sigma controls the width of the distribution. For different sigmas, the Gaussian distribution can be larger or thinner. So an infinity of Gaussian distributions exist with infinite possible means and infinite possible standard deviations. But they're all shaped like this in that they're all symmetric and they're all bell-shaped. This is a very common distribution that we will get extremely familiar with in the course of your urban studies. As I mentioned, when we talk about probability distribution for continuous probability distribution, what we can define is only the probability of something within a range. And for a lot of the uses of the Gaussian distribution, what we're going to want to define is the probability of a particular outcome being in the tail of the distribution, which means being above a certain value or below a certain value. Formally, to determine what that probability is, you're going to have to solve an integral, because again, these are continuous variables. In practice, you will never solve that integral. There are ways to, the integrals have been calculated and tabulated for you, and there are solvers in Python and the other languages that you will use that will solve the integral for you. But you should know that this is the way you find the probability of x being greater than a certain number, x being in this portion of the Gaussian distribution, or as well, x being in this region of the Gaussian distribution. This is something of great interest that will come up over and over again. Let me also mention that of great interest are the particular values of the standard deviation of a Gaussian distribution. A lot of times, as you will see towards the end of the lecture, we can approximate distributions to the Gaussian distribution, even if they're not really Gaussian. And if we know what the standard deviation of those distributions is, under the assumptions that they're really Gaussians, then we can tell what is the probability of something that we observe. We can tell if it was very, very improbable or if it was fairly common. We refer to the width of distributions in general and of the Gaussian distribution in particular with this parameter standard deviation, the sigma parameter. For the Gaussian distribution, 1 sigma contains 68% of the distribution. What that means is that under the area that is limited by 1 sigma being between 0 and this edge of this red rectangle, or this edge of the red rectangle, that's 68% of the area under the curve. 2 sigmas contain 95% of the area under the curve, and 3 sigma contains 99.7% of the area under the curve. It is very common, for example, to choose 2 sigma as a very important point, as a point where we start saying things are rare and exceptional if they are in the tail above the 2 sigma, and they're common if they are within the 2 sigma. So this will come up over and over again when we talk about p-values and hypothesis testing. So lastly, I want to talk about 2 important theorems that we will use during the course of our statistical inference. The central limit theorem is the first one. The central limit theorem says that any distribution, it doesn't matter if it's a binomial distribution or a Poisson distribution or even just a weird distribution that is not easily described with a mathematical function. But any distributions, as the sample size increases, so for example, as I can look at the height of more and more people, or at the number of floors in more and more buildings, as the sample size increases, the mean of those samples converges towards the mean of the population. Let's remind ourselves of the distinction. The population is the entirety of buildings, is the entirety of the human population if I'm measuring height. The population is all of the subjects that fall under the category that I'm probing. The sample is a subset of that I can put my hands on and measure, where I can measure and count the number of floors because they were tabulated by the city of New York and put in the Pluto data set, or where I can measure the height of the people because I had their medical records. So again, the central limit theorem says that the average of the sample converges to the average of the population if the sample size increases. So the larger my sample size, the better I can assess what the average of the population is. Here you have an example drawn from the binomial distribution, so 2 synthetic binomial distributions. In red, you have the population mean, the population mean, and in black you have the sample mean for 2 different sample sizes. A sample size of 20, so a very modest sample size, and a sample size of 100, a more substantial sample size, but still a small number. But you can see how the population mean and the sample mean are much closer when I have 100 samples, and the shape of the distribution is itself closer to the shape of the true distribution, to the shape of the theoretical distribution. Let me briefly, in words, mention the other theorem that we want to probe, and then move on to an IPython notebook where we will actually demonstrate this in code. The second theorem that I want to cover is the fact that the Poisson distribution, and really this is not only true for the Poisson distribution, but for many other distributions as well, including the binomial distribution, has a limit when lambda, in the case of the Poisson distribution, is large. The Poisson distribution for large lambda will tend to be to a Gaussian distribution. We'll start looking more and more like a Gaussian distribution. And again, in the case of the Poisson distribution, let's remind ourselves the Poisson distribution is controlled by a single parameter, lambda, which controls both the mean and the variance. Whereas the Gaussian distribution has two separate parameters, the mean and the standard deviation. If lambda is large enough for a Poisson distribution, the Poisson distribution will start looking more and more like a Gaussian distribution with mean lambda and sigma square root of lambda. Formally, this is true if lambda goes to infinity. In practice, this is true if lambda is a few tenths. Okay, let's move to an IPython notebook, which will allow us to work a little bit more interactively and see some of the concepts and some of the theorems that we want to explore in a hands-on fashion. The notebook, again, is available to you on GitHub. And right now, I have coded up all of the components, so I will do no real-time coding. I will just run the notebook. But I will highlight some of the important lines of code, and I do recommend that you look at the code line by line, and as well as maybe try to replicate some of the experiments, some of the exercises that we're doing here, maybe with different distributions or with different parameters for the same distribution, so that you make sure that you understand what we're actually doing. At this stage, all I want to do is give you an example of an application of a linear algebra method, of a linear algebra algorithm, to data science. Principal component analysis is a very, very common linear algebra method that is very commonly used in all sorts of data science disciplines. And it is extremely tightly close to the actual linear algebra method. What it comes down to is finding the eigenvalues and eigenvectors of a space of objects. In this case, we're going to use images, portraits of faces. And the usefulness of it is there are many applications. It allows you to compress the data by finding what is common to all the objects in your data set and what is peculiar about each one of the objects. And you can set a threshold at which you decide the accuracy is sufficient, and then you can describe your objects with a subset of the data. In this case, it's used for facial recognition. We will build eigenvalues in a space of images of faces, of portraits, and through the understanding of what is common to all faces and what is peculiar about one face, this method allows to do quite accurate image recognition. At first, I'm gonna, here you have some references. This is a reference to the original paper. This is a reference to the Rice eigenfaces group, where you can find more details about the algorithm and some of the math. But again, you don't need to know the math at this stage, although it is important that you understand what is the math behind an algorithm so that you don't use it as a black box, that you understand what is happening actually behind the hood. You are going to be actually applying the algorithm simply by importing a package in Python or R or whichever language you're using, and running a few lines of code, writing a few lines of code to apply the machinery to your data. The packages will do the hard work for you, but it is again important that you understand what work is being done to understand to actually interpret the result. So let me import a few packages. I'll import the NumPy library, which is a library that allows me to work with numerical arrays of numbers. The Pylab library, which is the library that we use to plot. Pill, which is the Python image library, I'm also importing. This library allows me to work with images so that I can load the portraits in and turn them into arrays of numbers to then use them with NumPy or scikit-learn, as we will see. So the first thing I'm going to do, I'm going to load the faces into memory. This will take a second if you download the notebook and do it for yourself. But this is the result. These are faces of the current cohort of CASP students. There's 81 portraits. Notice that the portraits originally are a little bit more than the face. They start at the waist, so I'm going to crop them. The place where I'm cropping them is here. I'm going to choose a width and a height of 80, a width of 50, and I'm going to choose the relevant region of the image that I want, which selects more or less just the face of the students. Also notice that images are typically three-dimensional objects. So when I store an image in the memory of a computer, I have 3 numbers for each pixel. Those represents the colors of the image, the R, G, and B channel. So each one of the pixels in the image, each location in the image, is expressed from the point of view of a computer as a series of 3 numbers, how much red, how much green, and how much blue I have. In this case, I don't care about the colors, so I'm going to take the average by calling .mean on that axis, on axis 2. I'm going to take the average of the 3 colors. So each image is now a 2-dimensional object, which has at each position, at each pixel, at each x and y coordinate, a single number. The next thing I'm going to do, I'm going to normalize the faces. We don't have to go into details as of why I'm doing that right now, but what I'm doing, I'm taking the average face, and I'm subtracting it from each portrait. This allows me to put all the data into the same frame of reference. Here you have the average face, the mean face for my data set, and here you have some of the portraits after I subtracted the mean face. Basically, this tells me how unique a face is compared to the average. Now, what I really want to do, the images are organized, image files are organized into rows and columns. This is because we want to perceive them as 2-dimensional objects. When we look at the word, we look at a 2-dimensional map of what we see. So we want to be able to perceive those images as points in a 2-dimensional space. However, the computer doesn't care about the fact that the images are arranged in rows and columns. So what I'm actually going to use for the principal component analysis is a flattened version of the face, where every row is basically attached to the end of the previous row. So it's a single string of object instead of being a 2-dimensional object. So my new array that I'm going to use goes from a dimension of 81 for 81 images, 80 for 80 pixels height, 50 for 50 pixels wide, to a dimension of 81 for 81 images, and 4,000 numbers, 4,000 being 80 times 50. So I've simply flattened out the images. Now they're better objects to work with from the point of view of a computer. Now here is where I run the PCA. And notice that all I need to do after all the math that takes to do this process is actually going to be done for me by the scikit-learn package. I'm loading a single package, a single module inside of the scikit-learn package. Scikit-learn is a common Python package to do machine learning tasks. I'm loading scikit-learn decomposition PCA, importing the PCA module, and I'm applying it to my data set with this line of code. So again, all of the math that it takes to find the eigenvalues and eigenvectors of a space is done for me by scikit-learn, and all I need to do is write 2 lines of code. This xvar is a variable that contains essentially, that contains
a number that corresponds to the importance that each eigenvector has in explaining my parameter space. And the way the eigenvectors come out of this package is ordered, so that the first eigenface, the first eigenvector, is the one that is describing the data set best. The second one described it the second best, etc. And the way I want to visualize it, I'm going to plot that number in the order in which the eigenvectors are come out of my scikit-learn package. I'm going to plot how important they are in describing the data set in a cumulative way, so that each number represents how well all the eigenvectors up to that one describe the space. So the first eigenvector describes 20% of the space. The second eigenvector and the first eigenvector together can explain 33% of the space, etc., etc. Now let's take a look at those eigenfaces, the eigenvectors of my parameter space. These ghostly images are my eigenvector. They're generally called eigenfaces, and effectively they represent what is common to all the faces in my dataset. And you can recognize some features. You can recognize the hair, you can recognize the eyes, you can recognize in some of them, at some point, glasses start popping up as an important element in the description of some of the objects in my space. Again, at the top, I'm plotting a number that corresponds to technically what we refer to as the variance in the data set explained by components up to that one. The first component explains 20% of the variance, and the second component explains 33%, the second and first component together can explain 33% of the variance, etc. And I'm plotting up to 90% of the variance explained. Now I can use these images to reconstruct images in the data set. The first image that I'm plotting here, I'm plotting 4 images. The first one is one of the images, one of my data points, one of the images in my original set. And then I'm plotting the same image, however, just this time reconstructed through the eigenvalues and the eigenvectors. I'm plotting the image reconstructed using all the eigenvalues and eigenvectors. Now, these should be identical to the original image, because if I use all of my eigenvectors, I can express any point in my parameter space. And then if I use only some of the eigenvectors, I can reconstruct the image to a lesser fidelity. Here using only the first 10 components, here using only the first 33 principal components, I get a less faithful reconstruction of my image. But you see how perhaps if fidelity, if an approximate reconstruction of the image is all I care about, then I can throw away some of the data and compress my data set and save storage space, but still maintain most of the information. The values associated with the eigenvalues represent what is peculiar about this space, and they're the method through which people use PCA eigenfaces to identify individuals in images. Notice that when I looked at my original data set, I mentioned that the cropping, the process through which I was selecting only the face out of the portrait, was rather rough. I simply selected a portion of each image where generally the face is located. This data set has an issue for this purpose, which is the fact that the faces are not aligned. And the secondary issue is that hair are shown in all of the faces. And the hair end up being a very, very important element in describing how peculiar one face is compared to the set. If I wanted to do this work more seriously, I would align the faces so that what I'm seeing, what is a change between an image to the next, really has to do with what's peculiar about that face and not with the position at which that face is portrayed. So here is the same process done with a dataset that was constructed for this purpose by the Rice Eigenfaces group, which collected images of the members of the group. And notice that the images are sometimes of the same member, that have members having being portrayed with different facial expressions. So this is a better dataset that really shows what is unique about a face and the facial expression vectors. Now, these should be identical to the original image, because if I use all of my eigenvectors, I can express any point in my parameter space. And then if I use only some of the eigenvectors, I can reconstruct the image to a lesser fidelity. Here using only the first 10 components, here using only the first 33 principal components, I get a less faithful reconstruction of my image. But you see how perhaps if fidelity, if an approximate reconstruction of the image is all I care about, then I can throw away some of the data and compress my data set and save storage space, but still maintain most of the information. The values associated with the eigenvalues represent effectively what is peculiar about this space, and they're the method through which people use PCA eigenfaces to identify individuals in images. Notice that when I looked at my original data set, I mentioned that the cropping, the process through which I was selecting only the face out of the portrait, was rather rough. I simply selected a portion of each image where generally the face is located. This data set has an issue for this purpose, which is the fact that the faces are not aligned. And the secondary issue is that hair are shown in all of the faces. And the hair end up being a very, very important element in describing how peculiar one face is compared to the set. If I wanted to do this work more seriously, I would align the faces so that what I'm seeing, what is a change between an image to the next, really has to do with what's peculiar about that face and not with the position at which that face is portrayed. So here is the same process done with a dataset that was constructed for this purpose by the Rice Eigenfaces group, which collected images of the members of the group. And notice that the images are sometimes of the same member, that have members having being portrayed with different facial expressions. So this is a better dataset that really shows what is unique about a face and the facial expression. And so if I redo this process with those images, I obtain eigenfaces that are more recognizably related to faces, to portraits. This is the mean face for that data set, which again is more closely resembles an actual face. I'm doing the same thing that I did before, flattening the images, applying the PCA with a call to scikit-learn package. And here are the eigenfaces generated with the new dataset. That's it. This was just simply an application of a linear algebra method to computer vision in this case. And it's just to give you an idea of how simple in reality it is to apply these algorithms, how you can apply them with a single call to a function, and how powerful they are. Please take a look at the details of the notebook. There's a lot of things that we will go over in the classes. For example, how to read and manipulate images, how to operate on arrays, to rearrange them, and of course, how to make simple plots, and